Welcome to the third session of Module 3. So in this session, I'll be talking about the third type of regression, which is polynomial regression. So we have already seen what is meant by linear regression as well as logistic regression. So if the relationship between the independent and dependent variables is linear, then we can use a straight line to fit the given data. So that is simple linear regression. So we can fit the data points using a straight line, which is the regression line. That will be linear regression. But what if the relationship between independent and dependent variables is non-linear? In that cases, we may not be able to fit the data points using a simple straight line. In that case, we have to use polynomial model. That is, if the relationship between independent and the dependent variables is not linear, then linear regression cannot be used as it will result in larger errors. This is the case. So here we can see that data points are not distributed in a linear fashion. So in that case, if we are going to draw a straight line of regression, then it is not at all coming near the data points. So in order to fit the data points properly, we may have to use some curves like this, which is going to be quadratic or more than that in nature. So that is the need of a polynomial model. So the problem of nonlinear regression, it can be solved by using two methods. One is we can transform the nonlinear data into linear data so that we can apply linear regression on that data. And the second method is to use polynomial regression. So we'll see both of them. So first is transformations, that is we have to convert nonlinear data into linear data so that it can be handled using linear regression method, simple linear regression method. So in that case we can consider an exponential function y which is equal to ae raised to bx. And how we are going to transform this? We can transform this by applying logarithm on both the sides. So ln of y is equal to ln of ae raised to bx. So that can be rewritten as ln of a plus ln of e raised to bx. And this is again changed into bx into ln of e. This is just logarithmic properties. Then this is rewritten as ln of y is equal to ln of a plus bx. So next is polynomial regression. So it can handle nonlinear relationships among variables by using nth degree of a polynomial. So instead of applying transformations, we may have to think what kind of transformations has to be applied in order to convert this nonlinear data into linear data. So to avoid such problems, we can directly make use of polynomial regression. It can be used to deal with different levels of curvilinearity. For example, second degree polynomial, they are known as quadratic transformations. So that is given as y is equal to a0 plus a1x plus a2x square. And third degree polynomials, they are known as cubic transformations. That is given as y is equal to a0 plus a1x plus a2x square plus a3x cube. So this a0, a1, a2, a3 all are coefficients of regression, and x is our independent variable and y is the dependent variable. So generally polynomials of maximum degree 4 are used, as higher order polynomials will take some strange shapes and it will make the curve more flexible. So mostly we will be going for polynomial regression up to degree 4. So here we can consider a second degree polynomial and see how we can solve it. So the polynomial equation is given by y is equal to a0 plus a1x plus a2x square. So the regression coefficients are a0, a1 and a2. We have to calculate it. So here I have used the matrix method for calculating them. Already we have seen in multiple linear regression how to solve the regression using a matrix method. So here A is equal to x inverse B, where x is given like this. X is n sigma xi square, again sigma xi square, sigma xi cube, sigma xi square, sigma xi cube, sigma xi raised to 4, and this is the B matrix. Sigma yi, sigma xi comma yi and sigma xi square comma yi. This is for the polynomial regression. This is how you will use matrix method. So here I have taken an example, a sample data set x and y. X is the independent variable and y is the dependent variable. So for polynomial regression, in order to calculate these values inside the matrix, just like we have done in linear regression, we have to make a table for simplicity. So here I have listed out x values, y values, and I need xi comma yi, that is there. Then xi square is needed, xi square y is needed, xi cube is needed, xi raised to 4 is needed. So all these things are listed as a column in this table, and we have computed the value. Sigma means you're just taking the sum of all of these, and just after that we can just substitute those values in this X matrix, and after taking the inverse, it is multiplied with this B matrix, so we will get this answer. These are simple mathematics. Then this is our A0, this is our A1, and this is A2. Just substitute it in the regression model formula. Y is equal to minus 0.75 plus 0.95x plus 0.75 x square. Now that is all about polynomial regression. So next is, if we are using these kind of models, so here I have taken linear regression, how to evaluate the performance of a linear regression model. After finding that straight line of regression, how we can evaluate that it is the best fit line for our data points. So for that, there are some performance evaluation metrics. So those are MAE, MSE, RMSE, relative MSE and CV. We will see each of these. There are formulas for each of these. So here I have taken a sample data set. So this is for predicting the sale of items. So there are two fresh items, say I6 and I7. Their actual values are 80 and 75, but the predicted value using the model is 75 and 85. So whether it is a good prediction or not, how we will evaluate it. So first is mean absolute error. First performance metric is mean absolute error. The formula for that is 1 by n sigma I is equal to 0 to n minus 1 yi minus yi cap. So we have to just substitute the values here. So yi is going to be the actual value, yi cap is going to be the predicted value. So for both the items I6 and I7, I have calculated MAE. So that is n is equal to 2. We have to check it for two test items. So 1 by 2 into 80 minus 75. This is for I6. Then 75 minus 85. This is for I7. And I'm getting 7.5. That is the mean absolute error, the percentage of error in the prediction. Next is mean squared error. The same formula with a square value. So just I'm squaring the differences over here and I'm getting 62.5 as the mean square error. The next is root mean square error, another performance matrix. We'll just take the root of mean square error, that is 7.91. The next is relative mean square error. Relative mean square error, this is the formula. So here I am taking the average of this y value. Okay, so finding relative MSE and CV, the training table should be used to find out the value, the average of y values that is taken over here. Just we need to find the each of these values and just substitute in the equation. We'll get the evaluation metric value. So here it is, relative MSE is 0.1219. Then last one is CV, which is coefficient of variation, that is RMSE by y bar. Y bar is the mean of these y values. So that is root of 62.5 by 100, which is 0.08. So these are different evaluation metrics that can be used to evaluate the performance of linear regression model, that is taken as per our requirement. So that's all for this session. Thank you.